We have talked about the angular momentum of systems of particles. Let's now talk about a particular system, namely rigid bodies. As a brief refresher, rigid bodies are objects that do not change their shape or deform in any way. We model them as a collection of point particles that have the same distances between them. The distances are not changing. We have two possibilities. We have a discrete case where the particles are connected in some way, and the point particles have their own mass. Or we could have a continuous case and have a mass density distribution for the particles having infinitesimal mass dm. As a reminder, rigid bodies are objects that do not change their shape or deform in any way as they move, whether they move rotationally, translationally, or in some combination of both. We can model rigid bodies as a collection of point particles that are moving together, where the distances between the point particles composing the rigid body do not change. And we have two different cases. We have a discrete case where we have a bunch of particles connected by thin rods, perhaps, or by forces that keep the particles in place. And we have the continuous case where we just have some sort of continuous object, and we treat each point of the continuous object as a point particle with infinitesimal mass dm, and keep track of the total mass using a mass density distribution. As a result of the rigid body condition, all particles that compose the rigid body move with the same translational velocity and rotate with the same angular velocity. With that out of the way, let's now calculate the angular momentum of a rigid body undergoing rotational motion. So first, we have to define a rotation axis using the angular velocity. I have denoted these in red for both the discrete and the continuous case. Each particle or point of the rigid body rotates around the rotational axis with the same angular velocity omega, as you may recall. Recall also for the discrete case, I am assuming that somehow the particles are fixed in place, either by thin rods of negligible mass or by some force. It turns out to be very complicated to calculate the angular momentum of a rigid body about a rotation axis. So we will make some simplifying assumptions that I will list in a moment, and I will go into more detail about those assumptions in another video. We first assume that the rigid body is purely rotating about the rotation axis. It is only undergoing rotational motion. The particles of the rigid body are moving in circles about it. There is no translational motion. We're only interested in rigid body rotation for this calculation. Mathematically, this means each particle of the rigid body has a total velocity of omega cross r, where r is the position vector from the reference point. This also means that we are calculating the angular momentum in a reference frame in which the rotation axis is fixed in location. The axis has no translational motion. We also will assume that the rotation axis is fixed in direction. Its direction is not changing. It is not rotating or changing direction. And per our first assumption, it is also not moving in location. It is simply fixed in space in the reference frame that we are calculating the angular momentum. Finally, we assume that the rotation axis is a symmetry axis through the center of mass. Or if the rotation axis is not through the center of mass, then it needs to be parallel to the symmetry axis through the center of mass. So if the red rotation axis is a symmetry axis through the center of mass, then these blue axes of rotation are legitimate axes of rotation we can use, provided that they are parallel to the red axes. Having made all these assumptions then, we are now ready to calculate the angular momentum of these rigid bodies. Recall that to calculate angular momentum, we need to do so about a reference point. So we will place the reference point on the axis of rotation. Recall as well that it is usually convenient to place the origin at the reference point. The reference point on the axis of rotation can't be anywhere along the line of the axis, but it needs to be level with the center of mass. So for example, suppose we have this cylinder here that I'm looking at an upright direction, and it is rotating about the red line. The red line is its rotation axis. Then the reference point about which we need to calculate the angular momentum needs to be on the rotation axis and on a level with the center of mass, which, since this rotation axis goes through the center of mass, means the reference point is at the center of mass. If, however, the cylinder was rotating about this new axis of rotation that I have colored in green, instead of the red, this axis of rotation being parallel to the red axis of rotation, then we need to place the reference point right here. So that way they are at the same level. There is no height difference between them. By contrast, if I place my reference point up there instead, it is no longer on the same level with the center of mass. So that would not be the reference point about which we are calculating the angular momentum. Again, I will go into more detail about this in another video about how to choose the reference point that makes the equations we are about to derive below true. So now let's calculate. The definition of angular momentum is r cross p, whether we work with the discrete or the continuous case. Recall that r is the position vector drawn from the reference point, which is on the axis of rotation and level with the center of mass, as already discussed. It is drawn from the reference point to the point particle. So we have an r cross p here, and same thing for the continuous case. We draw from the reference point that is on the axis of rotation, and we draw from the reference point to each of these infinitesimal masses located on our object. We then recall the definition of momentum. It is the mass times the velocity of each of these point particles. And so in the discrete case, we simply have the mass of each particle multiplied by their velocity as they are rotating about this axis. And we do the same thing for the continuous case. However, in the continuous case, they each have a small mass dm. I call it dmi, but it's really determined by the mass density function that we talked about previously. And since these are infinitesimal masses, the sum turns into an integral. And so this is what the angular momentum looks like in the continuous case. We then make use of the assumption that the rigid body is purely rotating, no translational motion. And as a result, we can use V equals omega cross R, recalling again that omega is the same for each particle on the rigid body. We do it for the discrete case, it's omega cross Ri for each position vector. And we do it in the continuous case, it's omega cross R, where now R is a variable that our mass density depends upon. And then, making use of our other assumptions about the axis being fixed in location, direction, and the symmetry axis assumption, we can reduce the discrete sum to I omega, where I is the sum of mi Ri squared, and to I omega, again, where I is now the integral of r squared dm. We have seen this before in the discrete case in a previous video, with this I here is just the moment of inertia. Well, here it appears again, the moment of inertia in the continuous case. And so we see indeed L equals I omega in both cases, where L is computed about a reference point on the axis of rotation, as discussed earlier. I is the moment of inertia about the axis of rotation. I is also known as the rotational inertia, another name for it. And R, in these formulas for moment of inertia in both cases, are no longer the position vector from the reference point to the various points of the rigid body, but instead r is the perpendicular distance from the axis to a piece of mass, dm, or one of the discrete masses, mi. As a reminder of what perpendicular distance means, take these two examples. One, a continuous case, a cylinder rotating about this axis of rotation. Another, a triangle rotating about this axis of rotation, where the idea is that this point is coming out of the page, then into the page, then behind a page. It's rotating about vertically. And I have denoted the center of mass, which is where our reference point should be, here and here. The perpendicular distance from the axis of rotation would look like this in the discrete case. So here's the perpendicular distance of this mass from the axis of rotation, or this in the continuous case. So here's the perpendicular distance from the axis of rotation to this infinitesimal mass element dm. Perpendicular, perpendicular. What I do not mean is something like the following. This line that I have just drawn is the line drawn from the center of mass to the particle or the small mass element dm. Notice it is not perpendicular to the axis of rotation. It is the position vector r for these particles, but it is not the perpendicular distance from the axis of rotation that goes into the moment of inertia formulas. So that's an illustration of what that means. And so now then, let's conclude. We have L equals I omega, but it comes with some assumptions. It is not true in general for rigid body rotation. It is only true for pure rotation of a rigid body about an axis that is fixed in direction and is along a symmetry axis, or, as I will talk about in another video more properly, a principal direction. And if it's not along the symmetry axis, then it needs to be along a symmetry principal direction, parallel to a symmetry principal axis. This gives us two cases to consider. The first case is when the axis of rotation is through the center of mass and is itself a symmetry or principal axis. In this case, the axis needs to be fixed in direction per our assumptions, but the center of mass can translate or accelerate relative to some other inertial frame of reference. It's totally fine for it to do that. L equals I omega will still be true, even though the body is not undergoing pure rotation in another reference frame. The other case is when we have a rotation axis that is through another point and is parallel to a symmetry principal axis that is through the center of mass. In this case, the axis must be fixed, not only in direction, but also in location. So no translational motion. It must be fixed relative to the body and also to an inertial reference frame. There can be no accelerations relative to some reference frame. So those are the two cases where L equals I omega holds true. I will discuss in more detail in another video about when this equation holds true. So these are the two cases that you can consider when L equals I omega may be used for the rotation of a rigid body. If, however, you're only interested in calculating the component of angular momentum along the rotation axis, for example, maybe it is the z-axis, we make it the z-axis, then we can use L equals I omega still for that component and relax the symmetry axis assumption. We only need pure rotation of a rigid body about an axis and the axis fixed in direction. We again have two conditions that arise. There's the case of having an axis. Now it no longer needs to be a symmetry or principal axis through the center of mass. And in that case, the axis needs to be fixed in direction, but the center of mass can accelerate or translate in any way relative to some inertial reference frame. Or we have an axis that's through another point. In this case, the axis needs to be fixed completely in direction and location relative to the body and also to an inertial reference frame. That's if you just want to use LZ equals I omega z. That's when that equation is true. There are more details that can be discussed, and I will discuss the exact cases in which these equations hold in another video. I will also just briefly note here that if you're trying to calculate the angular momentum in a reference frame where the body is translating, not just rotating, you won't be able to use I omega either. You will need to have an additional angular momentum component or translational velocity component that comes into play in order to calculate the angular momentum about that axis, which is moving in this reference frame. So we do need the pure rotation, but it's okay for the reference frame to be translating relative to another reference frame, or if it's an axis through the center of mass, it's okay for the reference frame to be accelerating relative to another inertial reference frame. Or in other words, if the axis is through the center of mass, it's okay for the reference frame to be non-inertial, in which we are considering this pure rotation of the rigid body.